Right, so hello and welcome to this video. I'm going to discuss about the layout pattern design I've chosen to implement in my CubeSat software, rather firmware. And it's going to be a relatively short video because there's not much design that is going on. I just thought I should, discuss how I've thought about this firmware. So the thing is that when you're designing a big project like this and you have like multiple layers of modules or systems, you have a lot of subsystems. Each subsystem has different components or subcomponents, and that subcomponent can or might have like multiple layers below it. It's very critical or crucial that you come up with like a very robust design architecture that will help you, number one, to make sure that your code can be maintained, number two, to make that it can be reused in other projects, so that in case you have a future project you want to reuse in your previous code, you can easily copy paste, for example, and change a few things. So the goal is like to reduce the number of things you have to change when you're trying to reuse your code. Number three is to make it portable. So what happens when you change your microcontroller that you're using? What happens when you change the hardware that you're using? What happens when you change, for example, the business logic, right? So basically what I'm trying to say is that your software or firmware should be as much or as decoupled as much as possible, right? So these modules, yes, should interact, but they should interact in a closed way. So each of these modules is considered or thought of as a black box, such that whatever happens inside the module is different. Not different, is not visible to the outer modules, such that if there's a change in the underlying layers, you don't have to affect the upper layers or the lower layers below that specific module. So this pattern is commonly known as the layered design pattern in embedded most of the time. Of course, it's visible or useful in other domains of software, games, whatnot. But embedded basically uses most of this, or rather uses this design pattern a lot. At this point, I just want to say that it's very early to like write this layered design pattern on a stone tablet, because a lot of things are bound to change. We are still in the process of developing, and a lot of these modules will be subject to change. So it's more of a hybrid approach at the moment, but basically this is what I'm going to use overall, right? So I'll just show you what I have here. I'll start from the bottom side. So right here we have, at the lowest level, we have the hardware or the physical layer, the actual hardware, physical hardware that can change. So these are things like the GPS modules, for example, right? The 5 volts and ground and whatever pins, GPIOs you are using. Yeah. So this is the physical hardware, things to do with like a sensor, light sensor, or something like an IMU or an accelerometer. That's the physical layer. I've called it. It's not normally called the physical layer, but hardware. Physical layer, I've just borrowed it from like the networking model. But that's that. From there we push, or rather we go up to the hardware abstraction layer, commonly known as the HAL. So STM32 has this HAL very robustly designed, and what it does is like it hides the abstract, right? It hides a lot of the underlying implementations from you, so that you don't have to, I will not say waste, but like you don't have to use a lot of time writing your own low-level things. Well, it's possible to write them, but sometimes time is more important than the fact that you can do it. right? So this is a hardware abstraction layer which has things to do with the, for example, the I2C, HAL I2C, SPI, UART. You know, this is going to be the HAL driven driver code for each module. So here is where we write the drivers. For example, for a GPS, this is where we write the driver for a GPS that has access to this hardware abstraction layer, right? So for example, I don't know whether I have the IDE open. Yeah, for example, if we are reading, this is a driver for the accelerometer. I'll make a video about how I wrote this. And for example, if we are reading the acceleration, right? So you see, if we want to read a register, for example, we have to call or reference the HAL, right? The hardware abstraction layer for I2C, for that part. So this is consumed, or this function is called by the driver code, right? For example, where is it? Here. It's called right there, right? And then the main.c then uses now this driver to read acceleration, for example. Okay, so that's a premature example, but it's fine. So the driver code is going to be, or rather be situated at the hardware abstraction layer level. And then after that, or on top of that, we have the FreeRTOS operating system. So this CubeSat is going to use FreeRTOS, and I've put this in a different layer that is going to use task-driven architecture to call whatever modules that have been written at the HAL layer, right? So for example, if we have a task that reads acceleration, right? Let's say X task read acceleration. That acceleration task is going to call whatever driver function that we have. So I don't know whether I have like a text editor, any text editor open. Let's see. I just want to like show you what I'm talking about a little bit. Test.c. Yep. Documents. Okay. Right. So I don't know. This is not like a real file. It's just to show you what I am saying. So if we have that, right? Let's say we have a task here that reads maybe X task read maybe accelerometer or acceleration. It's a task, so it's gonna take maybe some arguments, void pointer, right? So inside this task, obviously we have like a endless loop here, and now here is where we are going to read acceleration, right? Acceleration. So if we have a function that is called, for example, ADXL read acceleration, this is where we are going to call it, right? So whatever is called in this task is from the driver level, right? So we can have different tasks. X task maybe read I don't know, gyroscope, maybe gyroscope with a void pointer here, p, or arguments, or whatever you choose to call it for that, right? So here we can call another function. Maybe I'm using an MPU 6050 read what, I don't know, the angular velocity, right? For example, this is just an example code. Now the thing is, these tasks, as I've said, they are from the driver levels, right? And notice how I'm writing each of these functions starting with the module name: ADXL, MPU, ADXL read acceleration, MPU read that. So this I have a blog post about this, but this method of naming basically makes it very easy to search for a specific, I'll call it, component if you have a large code base, right? So this is what I'm calling the operating system layer, right? Operating system layer. Right, cool. Now the next thing is okay, before we go to the next thing, in the task driven architecture, we have what is called the intertask communication, right? So for example, this task will send to a given queue, right? To Q1, for example. This other task can send to Q2, right? To Q2. So these queues will be used to communicate between those tasks, right? You can have two ways. You can have tasks sending to different queues, or you can have tasks sending to the same queue. Basically, these are producers. Then you have consumer tasks down here that do something, right? Maybe aggregate that data or put it together, arrange it or something, right? So that's the FreeRTOS. The middleware is where the general functions live, right? Things to do with utilities, helpers, stuff to do like printf, maybe debug functions, unit testing code, filtering, state prediction algorithms. This is supposed to be a filter, also like a Kalman filter. You know, things to do with file access on the STM, like libjpeg for camera, fatfs for file system, etc. Right? So I don't want to like write a filter here on the driver. Reason being, this filter can be used for, or rather should be able to be used for different, or rather by different systems, right? So you can't couple or rather force the filter to only filter data from the IMU or from the accelerometer or from the GPS or whatever sensor you have. So you decouple it and put it in a given, you know, its own layer, right? So what happens is that whatever data that has been passed from this point to this point by a queue, it is also fed directly into whatever function you have here, maybe complementary filter, right? If it expects a linked list or a fee for buffer, right? Or a ring buffer, or whatever method you just use to pass it data to through your application or to the upper layers, that's what it's going to use. It doesn't care. It should not care about what type of data, not the type really. It should not care about where it's getting the data from. Its work is just to filter that and pass it on to the next, right? So that's that. This is supposed to be state prediction. Okay. Then debugging is, of course, we can write unit tests, or we can debug with the most common method, and easy one, but not professional though, printf, printing to the serial or whatever. We can use a logging module like, what's the word? It's MCU log or something. There's a common logging library, open source library for that, right? Then libjpeg, this is for the payload, is going to be capturing pictures and doing some functions on it. fatfs is for accessing files on the flash memory and on the SD card. And when you, for example, when you're accessing files from the SD card, you don't know where that data is coming from. Data was read from somewhere, it was saved into the SD card. Your work is just to fetch it, for example, right, and do something with it, right? So in here you'll find other interdependencies. For example, if we are filtering data that has been fetched from the SD card, then the data is not passed between two layers, it's just passed within the same layer, right? So it's not like how to say it, it's not standard, right? But it makes the work easier, the work done, right? So passing data within the layer is fine. There's no problem with that at all. Now, mostly, or rather what I intended it to be is that the middleware will do most of the work, most of the cleaning work. They'll do the organization, the cleaning, the packaging, etc. And then we pass, rather I want to pass data from all those subsystems to the application layer. Now, application layer is okay, I wouldn't say it's like most critical, but it's a critical part of it. It is going to be making decisions based on what we have received from the middleware. So we don't want to be receiving raw data here. I mean, here on the application layer, we want to be receiving raw data at the middleware or in the middleware level, clean it, package it, pass it over to the application layer, which does one thing: decisions. Right? So it's a CubeSat and you want it to have high mission reliability, or rather high reliability. So the decisions that it makes should be made from, rather how it did to approach it should be made from very, very clean and predictable data, right? So for example, should we turn off the payload, right? Should we activate the, maybe a magnetorquer, right? Or a reaction wheel, or whatever method we will be using. Should we, what else can we do? Should we detumble it? Right? Should we start transmitting data to ground or not? So at this point, we don't really care what hardware was used to read that data. We don't care about that. We just want to receive that data. It has to be there. And then we will be running the main finite state machine at this point. So this finite state machine is used to basically be a giant switch case, but or can be a function pointers. Oh no, I cannot use function pointers because if you have seen the NASA rule of 10, function pointers are not allowed for some reason. So maybe I should follow the same approach. So I can use switch case, maybe it's the easiest, or some state transition tables with some other hybrid. Anyway, I'll look into it. The point is, we run the main FSM here and do decisions. So if you remember from my last video that we have a decision engine somewhere. Where is it? Yep. So we have a decision engine on the OBC. This is running the core finite state machine that is basically aggregating data from all these other systems. See? Yeah. So where is it? Yeah, so that's it about the layered pattern. And you realize that I have these subsystems: ADC, OBC, EPS, etc, etc. Now, some of these have their own dedicated MCUs, STM32 obviously, and inside that system, for example, let's see the comms have its own dedicated MCU. So inside that, we will follow the same architecture, right? We will follow the same architecture here. So this abstraction layer is going to be placed on the OBC. Let me move this closer so that it's easier to navigate. Let me put it here. So this application layer is going to be running on the OBC. Yeah. It's going to be running on the OBC. Or if I change it, it can be in such a way that the application layer is running on any of the subsystems that have a dedicated MCU, and then it's passing a decision, rather an event. Just for example, the EPS does all of this and then tells the OBC, okay, turn off the batteries. If no, you can't turn off the batteries. Maybe stop receiving solar panel power, right? There is that architecture where the application layer is available in any subsystem that has a dedicated MCU, right? And then there is another architecture that has the application layer only on the OBC. I've not decided yet, but maybe it might be viable or not. We'll just experiment and see which works, right? Now the good thing about this is that a lot of things can be abstracted. We can have a standard method of how to say it, of extensibility. Is there anything like that? A method of how to expand something. Improvement. Let me just use improvement. Yeah. So what I'm trying to say is that you can have something like, I don't have a folder open. Let me open that folder. Let's say me just create a new one. Let's say playground. Yep, open this one, save. Cool. So what I'm saying is you're gonna have, yes, I trust. Oh no, I don't. I trust them. Transparent. Okay, so you're gonna have something like a, let's say main.c. Then I don't. Then you can say I want a config.h, right? Config.h. Now what this means is in config.h you can have defines, right? Define. This is, I'm borrowing the architecture majorly from FreeRTOS and most other architectures that I've gone through. So FreeRTOS has this, use, let's say, some module, use this, use that, use task inversion. I don't know whether that is a thing, but you can turn on and off system components, right? So let's say you have a struct, or rather a struct that says we have filters. No, I know filters, right? And on filters, let's say Kalman filter, let's say maybe complementary. There are a lot of filters you can use. Filter, let's say you want to use maybe a low pass filter with what? Low pass filter with exponential something, exponential averaging, etc, right? Now if I have a method here, what I want to have is have something like this. Define use maybe complementary filter, right? So I can have 0 here, I can have maybe a 1 and a 0, right? So in your main, for example, in the middleware, you can say now if use complementary filter, then use complementary filter somewhere here. So here you receive data and filter with that. You can actually receive data before you start just checking the filter. Filter with complementary, right? Filter with complementary, something like that. So you realize that this method will give me a way of testing different, if not all, types of filters without really changing anything. So I don't have to like separate code base for this, separate code base for that and that and that. No. I want to test all the filters and sample them, which one is the best, because I know like Kalman filter is what I'm going to use at the end of the day, but I want to see what happens if I use these other filters, right? So I don't know, here down here you can have something that, I don't know what it is, but something that checks that only one filter is selected, for example, just to improve system performance. If not one selected, maybe you can have like I don't know, it's some usage thing, usage message, just thinking, yeah, something like that, right? So by doing this, again, this calls the fact that you can decouple code, you can turn on and off software components, right? You can turn on and off software components. Where is okay, I'm going to show you something, but I will maybe in the next video. But yeah, so that's it about this, and this is the architecture I'm going to use. And what am I looking for? I'm looking for this. And yeah, let me know if you have any question or addition or improvement I can maybe include. Maybe if you have come across other patterns that will be or might be very useful to this design approach, let me know, and I'll appreciate that a lot. Right, so cool, have a nice one, and I'll see you in the next one.